the flame, right? And we know that's a light source. But the truth of the matter is, when we look at any particular object that's, lit by something, it's putting out light in all directions as well, not just the flame on that candle, right? Consider that. We can't see light rays when they're coming off to the side, right? There's light coming off of this light bulb, and it's putting out light in all directions. We can't see that light as it falls down and hits this ground, right?
Right.
We can't. What we see is the light coming down, hitting that floor, and reflecting back to us. So it's the ray of light that comes towards us from that piece of floor that we see, not the light that's actually coming through space. So the truth of the matter is, this part of this object is putting out light in all directions. So is every other part of the candle. Every part of the candle is putting light out everywhere as it reflects off of whatever ambient light there is. Okay, so that's an important point when we talk about how an image is made. Because, for instance, let's say we have a mirror, a planar mirror. Right? And we often just put a little line like this to say that this is the reflective surface on this side, and this is the stuff behind the mirror. And now, what has to be behind the mirror? There's no requirement on what's behind the mirror, right? It could be air behind the mirror. It could be concrete, solid concrete. It could be anything. So it's not important what's back there, but it is important that we can imagine that something's happened. That might, there's this virtual thing that happens with the possibility of light rays back there. So let's do this. Oftentimes when we draw these ray diagrams, we want to draw what we call a primary axis. And that's just something that's going to be perpendicular to the surface, the surface that we care about. And let's say I draw a candle. Okay? And you draw a candle, and we want to know, how is it that when we look at a mirror, that there's an image of us, all of us, on the other side, back here? Looks like there's something back here, right? Well, we once again imagine that every piece of this candle is putting light in all directions outwards, right? Make sense? Well, let's not try to draw every single ray that goes through every that comes out of every point of this candle. But let's draw some critical ones that are pretty important. What happens when a ray of light goes directly onto the surface, perpendicular like that?
Directly.
It reflects exactly back, right? Good. We can imagine that there's a virtual ray that continues on like this behind it. Straight and parallel. Now, let's do a little side exercise here. And if I have a ray that comes down like this on a mirror, and there's this angle theta, let's not use that angle. Let's use this angle. We always talk about the angle relative to the perpendicular most of the time. Well, which way is it going to reflect? It's going to reflect again at the exact same angle, right? This is what we mean by planar. A planar mirror does this. So I can draw any ray, because I know that this point comes down like, if I was to have this point come down like this, right? What would it actually do? It would reflect back this way at the same exact point, right? At the same exact angle. Sorry about that. And then what if I drew an array that was like this? They would also, if I drew this sort of, just as a guideline, a perpendicular surface, come down like this at the certain, no, that's not so good. I don't want to make that too parallel. A lot of practice with these ray diagrams. Do something like this, right? Same angle. So how does this this image form? Well, we're getting there. This point, where does this point form, the image of this little point that's putting out all this light form? Well, what we have to do is when it reflects, we have to do the same thing here as if we have this virtual ray going through. It's got to go through like that. There's a virtual ray that does this. Same over here. There's a virtual ray that does this. And they're all going to converge right at this point right here. So you're going to see this point, this light of that candle right there. You go, okay, well, that's one point. What about if I was, well, how about the rest of the candle? How do I know where the rest of the candle is? How about this the bottom of the candle? The bottom of the candle does this, right? Goes straight through. And it also can go upwards. And then what happens? It goes upwards at the same angle, and then it comes back down right over here. So the bottom of the candle is right there. And so that's the bottom of that image. So eventually, you can do this for every point on this object that's putting light out in all directions, and you can form this image, which is exactly the same image as on the front. And where is it? That image is behind the mirror, right? Now, it doesn't mean that there's no, like I said, there's no requirements that there has to be some space back there for this image to exist. It just looks like that image is back there from when we look at it. But there, we know that there's no actual thing back there, right? This is what we call a virtual image. It's purely based on our perceptions of all the reflections of this particular object. So this is a virtual image. All right, that's what that is. Now, so that's a planar mirror. So this is, we just talked about all this stuff. What's a real image? A real image is if it's this thing that doesn't require your perceptions to exist. And we'll talk about what that means in a bit. For instance, what's one thing that's a real image? Well, the image that goes onto a movie screen. The image that is going onto this screen from the lens and the light that's behind that particular lens on this projector. This is a real image, right? Because, it's kind of like a Zen koan, right? You can, if no one's there to perceive it, does it exist or not? Yes, this thing will exist if no one is here to look at it, right? Whereas the image of this candle, it doesn't exist. And unless you look at it, you won't see it. No one's going to see it. It's not going to be there. So that's what we mean by virtual versus real image. And we'll talk about how we can determine which is which. And one of the ways we do that is first we start talking about spherical mirrors. So, spherical mirrors. What is a spherical mirror? It's a mirror that has a shape like the inside or the outside of a sphere. What does that mean? It means it's got a constant radius. That curvature has a constant radius. It doesn't change its radius depending on where you are on that mirror. And so those things, those mirrors, and all lenses for that matter, have a certain way of characterizing them. And you might think that the way to characterize a spherical mirror, be it concave or convex, is by talking about the radius, right? And that's one way to talk about it, but a more important way to talk about it is what this term called F, the focal distance. So, what's the definition of a focal distance? It means when you have rays, light rays, that are perfectly parallel, coming towards this mirror, be it concave, this is a concave mirror, and this is a convex mirror. It's just language for depending on which way the thing curves and which side the reflecting surface is. And regardless of that, it's the distance away from the surface of that mirror when you have perfectly parallel rays to the primary axis coming down, and the ray will go through the focal the focal distance, focal point, same thing. So let's just do a different example where we have more rays than that particular example. Let's say you have this mirror, and here's your primary axis. You look at this thing and go, great. Here's a bunch of parallel rays coming through. By the way, if I have a bunch of parallel rays, what does that mean for the distance to the object from the mirror? How far away is it if I have parallel rays?
Infinitely far away?
Infinite, right? You gotta have something that is infinitely far away to have parallel rays. Because, once again, think about this little light source that's putting stuff out like this, right? The further away you get, the bigger this radius gets. If this radius is infinity, then it's pretty much a straight line, right? This is what we call planar waves. So you gotta have planar waves, and if you have planar waves, what happens is, all these planar waves, well, first of all, you know the one that's right on the axis is gonna come straight back. And then the one that's up here is gonna come down this way, and the one that's over here is gonna come down this way, and so on and so forth. And they will all converge right here at your focal distance. So anytime you have parallel rays parallel to the primary axis, it's got to come back through the focal distance. What if you have a convex lens? Well, in that case, you have virtual rays that go through the focal distance, because the focal distance for a convex mirror is inside that stuff, right, on the other side of the reflecting surface. Whereas for a concave mirror, the focal distance is on the inside, on the front side of that reflecting surface. So here you can see, for a convex mirror, you have parallel rays, and it will reflect back out that way, but you trace back the virtual ray, and it has to go through the focal distance there. Okay? So that's kind of how we define a focal length, or focal distance, or focal point. Those are all the same. And how does that relate to the radius? It turns out that the radius is half of the focal distance. Okay, so you think, well, why is that? How does that work out? Let's think about that. Here's this radius, right? And here's the center of my mirror, of my spherical surface. And if I put a ray out from the center of the mirror, what's going to happen? It's just going to come right back to it, right? No matter what I do. It comes right back to it. Now, does this count for, why isn't this the focal distance then? If I put rays out in any direction, then it goes right back to that center.
You're not coming out of it parallel.
Exactly. It's not coming out from parallel rays. So, sure, if it's not coming out from parallel rays, you put something out from the center, and it comes straight back through. So, then, how do we know where if the focal distance is? Well, let's do this exercise. Well, if this thing is coming parallel, this ray is coming parallel in, right? You get this angle over here. And what happens? Well, this is now the perpendicular, right? That's why this particular ray goes straight back.
Reflects off the same.
It reflects at the same angle, right? That's my focal distance. That's what happens when it's perfectly parallel. So because of the fact that you get the same angle coming down, you get half the distance. Right? So you make two of those arcs, make the full radius, and that's where you get your focal distance as being half of the radius. So that's where that comes from. And so we can easily, once we know what the radius is, we can easily get the focal distance and vice versa. Let's draw some ray diagrams. And this is what we want to do with drawing ray diagrams for mirrors. first step we want to do. Number 2. Draw a ray from top of object parallel to primary axis. Right? So, and then what happens after that? As a result of that, reflected ray goes through F, the focal point. Number 3. So actually, let's do each of these steps as we say them. So here's this mirror. So I draw my primary axis. Here's an object. I want to reproduce the middle of this plane right here. So the first thing I do is draw a ray that's parallel. And let's say F is right here. What's going to happen? It's going to reflect down through F. Right? That's the first step. That's the second step. The third step, so we're going to draw 2 rays. Draw a ray from the top of object through the center of the mirror. Here. And then what happens? The reflected ray comes back at symmetric angle to primary axis. So these are the simple steps, and believe me, who's got their textbooks? If you happen to look, you should open this up here, and if you look at some of these diagrams, especially you go all the way to figure 3411 on page 1018. You'll notice that there's a lot of different ways we can draw a ray diagram to make the image, to figure out how big the image is and where it is. All right? There's 4 different examples here. There's a bunch of different ways to do it. Personally, when I look at all these different ways, they're fairly arbitrary. Probably the part A is the least arbitrary, right? The A and C are the least arbitrary. But B and D, you just basically you're just making up any ray you want and hoping that you can draw this accurately, so that it makes sense. But if you take these 2 steps, it'll be guaranteed that you will get a pretty good sense of where it is, because these are really easy rays to draw. Okay, so what's this step number 3 say? It says, draw it to the center of the mirror, and you know that it's going to come back at the exact same angle, backwards. And the image is formed right here. So, image is formed where number 2 and 3 meet. So there you have this candle, and it's upside down, right? That's where the image is. Now, we call this distance P, and we call this distance I. That's just convention. P, I, and F. So we got 3 things that we want to talk about. P, I, and F. And so we can do some nice, easy, thin lens, spherical mirror approximations for exactly where those things are with this equation right here. 1 over p plus 1 over I equals 1 over f. Let's go to this worksheet. Now, I assume that Tony sort of goes through these in class somewhat, a little bit. Sometimes, not always. We're going to go through not all of it, certainly. We don't have that kind of time in one day, in 1 hour, but we'll go through this little by little. So it says here, number 1, sketch array diagram for an image formed by a concave mirror, including the object. So here that is. Okay, and it says, using this diagram in simple trigonometry, demonstrate that the ratio of the image height to object height equals the ratio of image distance to object distance. And under what conditions is this true? Now, we're not going to go through the gory details of this, but you can know, I'll give you guys a pretty good idea of how this happens by saying, well, here's this triangle. Here's this right triangle, right? And here's theta. Here is also theta. And here's the image right triangle.
Like similar triangles.
Similar triangles. That's exactly what we're talking about here, right? They both have the same angle. What does that mean? That means that the ratio of any two sides has to be equal for both of these triangles. Right, so that pretty much tells you how to derive that sort of thing by just arguing up by similar triangles. Well, the ratio of this distance divided by this distance has to equal this distance divided by that distance. Right, so the ratio of any two sides, any two same sides of similar triangles has to be the same. So what is this equation actually saying you're supposed to prove? It says that the ratio of the image height, let's make a name for these things. This is h of the object. This is h of the image, right? But h of the image height over the h of the object, right, equals the distance to the image, which is I, divided by the distance to the object, which is p. And it turns out that there's a minus here. And you go, where does this minus come from? Why did I just take that? Doesn't that sound arbitrary? I'm just going to put a minus in there just for kicks. No, it's not just for kicks. Look at this inversion, right? It's upside down. So if all of these numbers are positive, and all these numbers are positive, then you get that negative number because it's flipped, right? Because let's just say, in fact, that this is 0. You can even do it mathematically, say this is 0. Well, this way is positive, and this way is negative, right? So then hi better be a negative number. So that's one way of saying it. So it wasn't arbitrary at all, in fact, that I just stuck a negative in there. The other thing that can happen is that you can also, you can potentially have a positive ratio, right? This ratio, what's it called? It's called M, magnification. It's the size of the image divided by the size of the object. If the image is bigger than the object, you get greater than 1 magnification, right? It's bigger. It looks bigger than it actually is. You have magnification, you get positive magnification. So, that's positive, that's negative. There's another axis that we want to define as positive and negative. This way. Positive, negative. Right? So if you're in front of the mirror, it's a positive number. If you're behind the mirror, it's a negative number. And we're talking about F and P and I. So we gotta be careful about our signs. Careful of signs. Okay, you gotta be real careful about these signs because we will be doing some stuff where things are negative. Okay, so this is how we draw it for a concave mirror. So let's do a couple examples here. It says here, an object has a height of 1.5 centimeters and viewed through a concave spherical mirror. F equals 5 centimeters. Determine the location, height, and orientation of the image for the following distances that the object is held away from the lens. Verify your calculations using crude ray diagrams. I would start with the crude ray diagrams first. Okay. So I'll do one. I'll do the first one. I'll have you guys do the next one. Does everyone have this? Can I erase this? So here's where you pull out your ruler and start using it. Okay. It says here that the mirror has an f5 of 5 centimeters. So whatever this mirror is, let's say I have f of 5 centimeters. F is right here. Right. So I go f is 5, this is 5, this is 10, 15, 20, 25, 30, is that 10, 20, 30, 35, right? So I got an object that's, oh, it says it's 1.5 centimeters. That's pretty small. It's going to be like that big, right? Let's just make it a little stick that sticks up like that. About 1.5. That's probably bigger than 1.5. That's probably more like 2, but this is rough. So it says, determine the location, height, and orientation with a crude ray diagram. So what do I do first? I draw first one ray that's parallel, and it's got to go through the focus, right? And then I got to draw one ray that goes through to the center, and that's a pretty shallow angle, right? It's going to come back at the same shallow angle. So here's my stick. So what should I expect? It should be somewhere between 5 and 10 centimeters away, and it should be upside down, and it's going to be smaller than the original object, right? So this is just the general, this is why we do these ray diagrams, so we can get a general idea of what we're going to get. So then you put it into this equation, right? 1 over P plus 1 over I equals 1 over F. Great. 1 over 35 centimeters plus 1 over I equals 1 over 5 centimeters.